All right, some random chemistry questions to get us on track. And then we'll talk about problem 4. And we're going to talk more about how to do more calculations with the periodic table. First question is basically, why do we spend so much time and energy and money on making new elements on the periodic table when they have half-lives that are measured in the milliseconds? So they basically disappeared. We don't really there's not necessarily a tangible benefit to doing science sometimes. You don't necessarily know what the applications are going to be. So part of it is what they call science for science sake, which seems like it often gets, especially when money gets tight for the government, scientific grants and scientific funding, it's one of the first things that people try to cut because it's hard to point to something and say it's going to pay off. Because it doesn't always, but it always increases our knowledge of the universe, and there's sometimes it pays off way beyond anything we could possibly have imagined. Carl Sagan has a good story where he talks about the importance of funding science for science sake, also called pure science. If you had gone back to the 1800s, and in the 1850s, you had told somebody that the only funding for science in the UK is going to be for this one project where we're trying to make it so that the voice of the king can be heard in every single house in England at the same time, or even worldwide. If they just said that's the only thing we're funding is this project, they could have never actually gotten there because they didn't have the pure research. They were funding this guy named Maxwell, who eventually came up with some of this math to describe the way that radio waves work, that became known as Maxwell's equations. And there was no practical application for it at the time. But less than 10 years later, it turned into radio. Without funding for pure science, we wouldn't have things like radio. And the same is true for things like going to other planets. We don't necessarily know what we're going to find. That's why we're going there. And so funding for things like that wind up being really important. It's things for like making these new elements. We don't necessarily know what properties they're going to have. We can guess. We have an idea that there should be some relatively stable, meaning they'll still be radioactive, but they'll have half-lives in the measured in years or decades probably. Around atomic number 120 to 125 or so. But until we make them, we won't know. And they might have really useful properties. It's predicted that they'd be super dense, very, very good conductors, that high degree of metallicity that we talked about the other day. But until we make them, we don't know. So funding for pure science and just doing things just because they haven't been done before and because it's going to help us understand the universe winds up being really an important part of doing science. And it's not until we get the science that we can do the engineering with it. And the engineering is let's take something we know and find an application for it. Building stuff is not really science, that's engineering. Even if you're building something that's going to be used for science, that's the fact that you're taking something and making something out of it. That's actually the engineering part. So that's one of the reasons why science and engineering are so tightly linked, is because they work together. If you get a degree in science, you're going to have to be able to do some amount of engineering as well, because there's some amount of problem solving and building that happens in labs that you have to be able to work with. It wasn't just scientists that built the particle accelerators in Switzerland and in Liverpool. Maybe there's a particle accelerator there too. But it was engineers working with scientists. Scientists said, we need to be able to do this. Can we take the existing technology and build something with it? The engineer said, yeah, I think we can do that. So it's always an interaction between the different fields that actually makes really interesting things happen. Somebody asked, do elements have different characteristics in space or on that International Space Station? For the most part, the individual elements, no. In fact, that's actually one of the only ways that we can study distant planets and star systems and things like that is by assuming that the laws of physics are constant throughout the universe. We don't know that for sure. And there are some interesting things. What is different about space is things like growth of crystals. Growing crystals in zero gravity or synthesizing chemicals in zero gravity can be markedly different. So there are some things that are different about low gravity environments. In fact, that's actually one of the biggest obstacles to having self-sustaining settlements on other planets or even just on space stations is that things grow differently, plants grow differently, mice reproduce differently, which means probably human reproduction is going to be affected by low gravity and microgravity, which means putting a colony on the moon is not as simple as it sounds. Because if you can't have children, raise children, it's not really a self-sustaining colony. It's more just like a station in the Antarctica. And actually, Antarctica is a lot easier to settle because at least it has the same gravity and air. So there are some different things that are different. And obviously, I like talking about space and have thought about this a little bit. I just finished reading a book about why settling space is really not in the cards in the near future, despite what Elon Musk says. And one of the big things is because we just don't know about how it's going to affect long-term microgravity or low gravity might affect humans or human development. And then I like this one because I have a clever answer for it. Technically, we all have the same favorite molecule. Technically, the only thing you enjoy is dopamine. So everybody's favorite molecule is dopamine. If you're unfamiliar with the term, dopamine is the molecule that is basic. It's linked very strongly to a sense of reward. I'm trying to think what the exact cause and effect and reward. Basically, when you complete something and you get that rush of feeling good that you finished something, you hit end or hit submit. That's dopamine. And basically, it's really closely tied to learning repetitive motion or behaviors. So that's why positive reinforcement works so well with kids and with small animals that you're training. It's because of the dopamine. And that's everybody's favorite molecule. All right. I also, just a caveat, we don't know collectively as a species, we don't know very much about how the brain works. So I can say things like everybody's favorite molecule is dopamine because it sounds clever. We don't actually know all of the pathways and all the different ways that our neurotransmitters interact. Turns out it's a really, really, really complicated system. We think that dopamine is about the simplest of the neurotransmitters with that sense of reward. But it's tied to every other molecule in your brain in some way. And so all of those neurotransmitters, we can say that they're linked things, but we really don't understand them at a scientific level, at a cause and effect level, where we can say things like increased serotonin means less depression. All we can say is that when we give people selective serotonin reuptake inhibitors, their depression symptoms go away, but that doesn't necessarily mean it's the serotonin that's doing that. So cognition and consciousness is really complicated. And while it is definitely tied to molecules and chemistry and genetics, it's really, really hard to say definitively this one thing over here is the cause of mental illness or this particular disorder or this particular emotion or feeling. It's really tempting to be able to oversimplify, so we have to be careful not to do that. These two questions are tied together. This was the question from question 4, right? How many neutrons are present in 6.501 times 10 to the 18 atoms of calcium 41? If we know it's calcium 41, and we're trying to find neutrons, we start by just looking at, okay, well, if I know that this is the isotope and this is the element that I'm dealing with, we can count protons, neutrons, and electrons. And so we can start by saying, okay, for calcium 40, 41, sorry. That's gonna be, it's calcium, and calcium always has an atomic number of 20. So we know it's got 20 protons. And we know that the total mass is 41. So 41 mass number, or 41 AMU for atomic mass unit. We're gonna do some more with these units and masses today. And we know that 20 protons, every proton is 1 AMU within sig phase. 1.0078 or so actually, but close enough to call it 1. That means that every 1 atom of calcium 41 equals 21 neutrons. Now, when I'm showing my work for this, and this is the step that most of you were missing on the quiz, is you got the right answer. Because you could look at this and say, oh, I've got this many atoms, and every atom has this many. We want to show this as a conversion, because this is an equality, right? Anytime we can say these two things are equal to each other, we can write it as a conversion too, right? So the way that I would show it, and that I didn't mark anybody down for this, but this is going to be really helpful in the future, is to continuously show our work as conversions. Well, anytime you're multiplying by a number like that, write it as a conversion. So 6.501 times 10 to the 18 atoms of calcium 41. And for every 1 atom, that's 21 neutrons. Atoms cancels out with atoms, we're just left in neutrons. Almost everybody found a way to figure out that they're supposed to just multiply by 21. Here's how you show your work. All right, and as I mentioned the other day, AI bots don't show their work that way. So if you want to be sure that I'm not going to think that you're using ChatGPT, show your work the way we do it in class. Again, I'm not going to take away points unless it's wildly different. One that I've run into before is ChatGPT actually got the right answer for once on one of my test questions. But they did it in units that I had never taught my students. And in units that they didn't understand what they were actually writing. They copied the numbers down, did the math without understanding what they were doing, which for this class is our definition of cheating, is when you turn in something you don't understand. I don't care if you got the right answer, if you did it the wrong way, and it becomes really obvious when you show your work differently. And sooner or later, I'm going to be able to stop talking about AI, but I'm just reminding everybody, the more you can show your work the way we do it in class, the easier it is for everybody, and the less I have to worry about it. I know that I've made my point in this class, and nobody in this class is using AI for any of this stuff. But it's something that I've spent way too much time thinking about in the last several years. So I'd like to think about it less. So our final answer winds up being something times 10 to the 20, right? Who's got the final number? Times 10 to the 20 neutrons. Okay. So one of the things we're going to actually continue to do here is we'll find out that basically the periodic table is a giant table of conversions. It's just conversions that are specific to certain types of matter, because we can always write, if I asked you to do the same thing for protons, if I said, okay, how many protons are in let's use lead. If we had 1.5 times 10 to the 15 atoms of lead, how many protons is that? Well, as long as you have your periodic table, you can do that. Do we need to know what the isotope is of the lead in this case? Why not? Because isotopes affect what? Are based on what? The other one. Neutrons. Ions are based on electrons. Isotopes are based on neutrons. If I'm asking about protons, all we need to know is what the element is. Right? Because elements are based on protons. So your periodic table is going to let you write a conversion for this. Because we can say every 1 atom of lead equals 82, I think, protons. There's our conversion. So 1.5 times 10 to the 15 atoms of lead. Every 1 atom of lead is 82 protons. So we're going to get something times 10 to the 17. Something like 1.23 maybe. Times 10 to the 17. Protons. How many sig figs do we get to keep though? I wrote 3. So is 82 an approximate number? It's exact, it's a counting number, right? The definition, we can't have part of a neutron or part of a proton. So when we're counting protons, that's an exact number. Because we're counting things. If we were off by a proton, it's not lead. So the fact that we know it's lead means we know it's exactly 82 protons. But we only had 2 sig figs there. So yeah, it'd be 1.2 times 10 to the 17. There was one more thing I was gonna, this does translate nicely into this. Well, let's finish up with our classification of matter because there's only 2 slides on it. This is kind of where we ended the other day. Remember I just said we're going to define a bunch of vocab real quick. We ended talking about the difference between elements and compounds and mixtures, right? Our mixtures versus compounds, elements were pretty straightforward. An element is just anything that's in its pure state. Anything that's made up of just a single element in its natural state on Earth. Which does get a little tricky in some cases, but for the most part, that means we're talking about something with the charge of 0. And it's only one element. So if I said iron metal as a solid, the charge of 0 indicates that it's a metal. Well, for iron. Charge of 0 means it's in its elemental state. As soon as I take this pure iron and I add something else to it, it's not elemental iron anymore. Right? So for instance, what happens when you leave iron outside in the winter? It rusts. When it rusts, it's turning into iron oxide. That's no longer pure iron, right? So it's not in its elemental form anymore. Now it's a compound. We're getting ahead of ourselves a little bit because we're not gonna talk about reactions for a little bit still. But this reaction is two elements, iron as its in its elemental state and oxygen in its elemental state, reacting together to make a compound. Right, so this is our first example of what we call a chemical change. A chemical change is anytime we're making a new compound or even making an element. If we started from rust, if we actually apply voltage to it, if we hooked it up to a car battery properly, we can turn it back into iron, metal, and oxygen gas. That would still be a chemical change because we're changing what compounds are present in our system. And so anytime we change the compounds we have or the elements that we have, that's a chemical change. If there's a chemical change, there's probably a different sort of change. Oh, there it is. I knew it was on here somewhere. Anytime that we're making a change to a system, but we're not changing what the compounds and elements are, it's a physical change. Right, so we talked about the difference between mixtures and compounds. We said that mixtures you can easily separate using physical methods, right? We talked about salt water. Can you separate the salt from salt water without changing what anything is? Yeah, it turns out it's not too tricky. You let the water evaporate, the salt is still there, right? So taking salt and dissolving it in water, it's a physical change. Taking salt water and evaporating the water to get back to being to salt is a physical change because we didn't change the identity of anything. We just changed how they're mixed together or not, as the case may be. Right, and then we ended with talking about these two terms, homogeneous versus heterogeneous. Homogeneous just means evenly mixed. Means if you took any sample from the top or the bottom or the middle, it's going to be the same composition, no matter where you take the sample. Which is kind of hard to define actually, because it kind of depends on what scale you're working at. One of my favorite examples is milk. Is milk a homogeneous mixture? First off, is it a mixture or is it a pure substance? Mixture. How do you know it's a mixture? Water. It's got all sorts of stuff in it, right? And we know we can change the concentration of some of those things because what kinds of milk can you buy that are still dairy milk? 1%, 2% whole milk, right? So obviously there's at least one component we can take out and it's still milk. But the fact that we can remove one component of it without changing it, well, that much, tells us that it's a mixture. Is it heterogeneous or homogeneous? I mean, it says homogenized in the label, right? But it depends a little bit how far you zoom in. Right? Because yeah, it's homogeneous. If you take a drink of milk from the top of the glass, it's going to taste the bottom the same as milk from the bottom of the glass, mostly. But if you zoom in far enough, the reason it looks milky is because it's actually got little droplets of protein and fat suspended in the water. That's actually what makes it so it diffracts the light, so that light bounces off of it and it's opaque, is because it looks. If you had a big glass of milk and you zoomed in far enough, you'd see these tiny little droplets floating around. And those tiny little spheres of protein and sugar and calcium and fat and stuff like that, they scatter the light. Because anytime you get light moving between substances, it bends a little bit. And so when you have all these tiny little spheres suspended in water, they scatter the light really well. So it's not truly homogeneous because it has these little droplets. If you pulled out a really strong microscope and put a drop of milk on a slide, you could probably see the different droplets that are suspended in the milk. So it's homogeneous at the macroscopic level, on the visible level, but if we zoom in far enough, it's not really homogeneous. So I like to use this as an example. I want you to know these terms, but for the most part, I'm not going to grade you on getting things right on this. The way that I usually grade, if I said, is milk a homogeneous mixture on a test, these are both right answers, as long as you explain what you mean. If you say it's homogeneous because the taste of the milk from the top of the sample is the same as the taste of the milk at the bottom, that's a full credit answer. If you said it's heterogeneous because it has little droplets floating around that are not completely mixed and dissolved, that's also a full credit answer. It's more about context than it is about knowing one right answer, which makes it hard to write and grade questions, and it means that you don't necessarily know what to expect as easily. It's not as easy as just memorize the answer to is milk a homogeneous mixture. You have to understand the system a little bit and be able to explain it a little bit. The good news is, as long as you explain your logic, even if you're wrong, if you can explain your logic, I can give lots of partial credit. Your logic is at least rooted in reality somehow. All right, let's talk about different kinds of chemical and physical changes. So again, this is another case where if you argue it properly, you could say that they're all both. If you're mostly. You may notice I don't like using absolutes. There's a lot of, well, usually or generally, sometimes. All right, let's talk about these changes. If we take sugar and we dissolve it in water, is that a chemical change or a physical change?
It's like 3D.
Mostly physical. We usually consider that physical because if we evaporated the water back out, we could get the sugar back. It depends a little bit. The more you know, the more complicated everything seems, though, because if you dissolve table sugar, sucrose, in water, if there's even a little bit of acid to that water, you actually take the sucrose and you split it into glucose and fructose. And then when you evaporate the water back out, you will get a little bit of both of those instead. And so it won't necessarily be the exact same sugars back that you started with. But for the most part, when we talk about this, we'd assume we're talking about a physical change. Iron rusting in an old car, chemical, physical. Can't really undo it, right? How do you, anybody ever restored a car or had to deal with rust in a car? You can electroplate it to try and turn the rust back into iron. But if it's just surface rust, the number one thing you do is you just sand it off. You just get rid of it. Don't worry about it. Which would be another physical change. Instead of trying to turn the rust back into iron, you scrub it off, and now you have rust as a dust instead of attached to your metal. That'd be a physical change. What about burning a candle? Physical, why?
Okay, I said chemical.
Sorry, chemical, why?
I just learned that whenever you're burning something, you're chemically changing.
Okay, somebody else said physical.
So it's still,
It's still a candle. So this is another one where it's the burning part is chemical because you can't undo it. You can't unburn a candle. But there's a physical change associated with that because the wax melts. And phase changes, like going from a solid to a liquid, are physical changes. So there's really two things happening when we burn a candle. The wick in some of the wax is burning, turning into CO2 and water, but some of the wax is just getting hot, melting. and that's a physical change. So anytime you see words like burning or rusting, those are gonna be chemical changes. When you see phase change words like melting, evaporating, dissolving, those are usually physical changes. So ice melting. Physical, it's still water, right? Before and after, it's still water. Toasting a marshmallow. Can you untoast a marshmallow?
No.
If you can't undo it, that's a pretty good hint that it's probably chemical. It is also one of those ones where, well, the middle is getting all soft and melty. You could call that a physical change because when it cools back down, it kind of re-solidifies, right? A little bit. How about propane burning? Uses the word burning, right? That's one of our hints. Yeah, propane burning is gonna be a chemical change. What about dry ice? It uses the word melting, which I told you was a sign, but it put it in quotes, which made you double think it, right? It is a physical change, it's just a weird one that we're not used to. Does anybody know what dry ice is? Close. Carbon dioxide. Frozen carbon dioxide. So what happens with dry ice? When it's solid CO2. When you let it warm up, it doesn't go to a liquid, it turns straight from a solid to a gas. We'll talk about why that happens specifically to CO2 a little bit after the midterm, when we spend more time on phase change. But basically, it's not really melting, because melting specifically means a solid turns to a liquid. This is a different type of phase change that we don't see that often on Earth, called sublimation, where you go straight from a solid to a gas, but it's still just a phase change. And if you captured that CO2 as a gas, you could actually turn it back into being a solid. Again, without ever necessarily seeing a liquid. You can actually make dry ice at home. If you have a CO2 canister, if you can fill a container with CO2, basically you just crush it really, really hard. And you get CO2 will turn back into being solid CO2. So you can make dry ice that way. A lab that I used to work in we had basically, it was like a canister with a vise on top. It's like a piston that had a moving piece with a vise on top. And so we would fill it up with CO2, crank the vise down, and literally just compress it until it turned into a solid, and then we had dry ice. But it was really just a physical change, because as soon as we removed that extra pressure, it started turning back into a gas. Right? It's pretty easy to go back and forth between those. I saved this one for last. Is cutting a pizza a physical change or a chemical change? Physical seems like it makes sense. It's the same compounds before and after. It tastes the same before you cut it and after you cut it, right? But you can't uncut it. So it's a little bit of both. Well, we're finding out here is there's a lot of gray area in chemistry. Turned out the easy answers in the sciences are usually wrong. The more you know about a system, the more you realize that there are no simple answers.
We just lack the technology to untoast a marshmallow, or is there an actual?
Actually, I think some people won the Nobel Prize a few years ago for they win the Nobel Prize, or were they just nominated for unboiling an egg.
Yeah, okay, so.
But they weren't able to take it all the way back to something that could still turn into a chicken. But they were able to take I don't know if it was hard boiled, they were able to take an egg that was cooked and undo a lot of the processes, but those were chemical changes that they were undoing. Turns out chemical changes can be undone. It's just a lot harder. Like unrusting the iron in a car takes a voltage. You have to, it's a lot harder than just changing the temperature or something like that. So for cutting a pizza, what you're actually doing when you cut the pizza crust, like you could, it's definitely a physical change in terms of the cheese, right? You can always remelt cheese and have it stick back together. But you can't fix the crust that way. Because what you actually do when you're cutting the crust is you're using physical pressure to break apart proteins that form the gluten in the crust. And those gluten molecules or whatever, there's a lot of any grain is going to have something analogous to gluten, even if it's not wheat. Those can't be put back together. So we're using physical force to pull apart chemical bonds. And that's something we can't easily undo once they're cooked. You can let gluten molecules reform. If you take a ball of dough and you pull it all the way apart into two pieces, you can knead them back together and turn it back, and you can let those gluten molecules reform. But as soon as you cook it and you remove all that water, you remove the ability to do that. So this is definitely one where if this was on a test, both the right answers as long as you explain yourself properly. Right? Remember that the point of the test is not to get right answers, it's to show me that you understand concepts. Right? I care less about you getting the right answer. If you get even on something like a conversion word problem, out of 10 points, if you show your work, show me you understand how to do everything properly and get the wrong answer, that's still 9 out of 10. In fact, if you don't even hit enter on your calculator, if you forget your calculator and take the test without a calculator, you can still get a 9 out of 10 on a lot of these problems, because as long as you set it up right, I don't care that much that you know how to work a calculator. That's a learned skill. I care that you learn how to set it up right. And same is true for some of these questions, okay? All right. Couple more things before break. Let's go back to talking about atoms and doing conversions with them. It's really hard to visualize what 10 to the 20th is, right? Like on a piece of paper, you could write out 1, 1, 3, 6, 5, followed by 17 more zeros to get an idea of how big this number is. But what does that look like in terms of objects? Can anybody visualize what 10 to the 20th ping pong balls looks like? It's just so far beyond what our brains are evolved to be able to handle that we don't actually think in terms of scientific notation very well once we get past a certain point. Once we start getting to these really, really big numbers, it gets really, really hard to actually physically visualize what's going on. So one of the things that we do is we basically have a way of counting atoms that's not just counting individual atoms. We group them together in larger numbers. Those larger numbers, come back to that in a second, are called moles. Not like the furry rodent, but it's easier to picture a furry rodent than it is to picture a mole of anything. A mole is basically the way that we count atoms so that we can actually have a physical amount we can measure. So does anybody know what a mole is, what the number is for a mole? 6. 6 point. Also called Avogadro's number, after the scientist who first defined it. Basically, when we're dealing with something as small as an atom, we can't count individual atoms, so we count them by groups, and this is a convenient number for counting. Why did they choose this number? Basically, because at the beginning, when they were first figuring all this out and first looking at the periodic table, they said, okay, well, hydrogen's the smallest atom that we have, smallest element we have. So we're gonna take 1 gram of hydrogen and we're gonna estimate the number of atoms in 1 gram of hydrogen. And then we're gonna call that number a mole. They chose the word mole because it's similar to molecule, not because they were fond of rodents. It was a convenient shortened way of writing molecules. So they said a mole of something was this number. Now, later on, as they added more sig figs to the periodic table, they figured out that hydrogen is not the best way to do this. They basically redefined this number a little bit based on carbon rather than hydrogen. So technically now a mole is the number of atoms in exactly 12 grams of carbon 12. So we still needed a way to estimate that, but we're able to do that without too much trouble. Once you start factoring in, we can count protons and knowing the periodic table. But basically, this is gonna be the way we count things. And when we say we have a mole of something, if we have a mole of eggs, it's just like saying a dozen eggs. Mole is just a counting number and we use dozens all the time because we're used to thinking in dozens for a lot of things, right? A dozen cookies, a dozen eggs, a dozen whatever. You can have a dozen students, right? This works the exact same way, it's just a much larger number. So just like we can say 1 dozen eggs equals 12 eggs, we can say 1 mole of hydrogen is 6.02 times 10 to the 23rd atoms. Right, so it's just a way that we can count these things conveniently. Because when we have a mole of any of our elements now, that's something that we can weigh out. We can go into the lab, we can go to the scale, to the balance, and we can weigh out a certain number of grams. And we can figure out how many moles that is.
Exact number.
It would not be an exact number. If you took it out to 23 decimal places, then yes, it would be an exact number. But unless you're writing out all 23 digits, it is a measured number. Which I'm not even sure. I know that we can take it out to like 10 decimal places. I don't know how far if it's ever been done all the way down to individual atoms. Maybe. All right, so how does this help us on the periodic table? Because I still didn't say anything about the grams yet. This is just how we count atoms. If we want to actually bring in masses and go back to this question here, why is atomic mass not being used? We didn't use atomic mass in this question because we were talking about a specific isotope. But if we're talking about a mixture of isotopes, like say the one that we find on the periodic table, it turns out those atomic mass numbers on the periodic table are going to be tied to this idea of moles. And because of this, I kind of got these out of order a little bit, based on how I wanted to talk about them today. The other unit that we use that we have a conversion for is atomic mass units, or AMU. It turns out those are the units that are actually on the periodic table under atomic mass. The atomic mass of carbon is listed as 12.011. That's in atomic mass units. Which means we can actually take that, we can use this conversion to figure out how many kilograms and then how many grams or nanograms or whatever we want. After that, but we're still talking about things in atomic units, talking about individual atoms when we do that. And even if something as large as this is a very large protein. A protein weighs 4.72 times 10 to the 5 AMU. That's not an unreasonable size for a protein. It's fairly large. But if we want to know how many grams that is. Well, we can use this conversion and say, okay, well, 1 AMU is 1.661 times 10 to the minus 27 kilograms. And if we're trying to put it in grams, we'll go one step further. What's our next conversion if we're trying to end in grams? Yeah, we're gonna want kilograms on bottom, right? And 1 gram or 1 kilogram is 1,000 grams. Well, without even doing the math, I'm gonna get something like 7 times 10 to the minus 19. A really, really small number, right? It's still something that we can't measure on as large as this protein is, we still can't measure it on a scale in the lab. Right, so this number, remember that I said our definition of Avogadro's number of that 6 times 10 to the 23rd came from the number of atoms in exactly 12 grams of carbon-12. Well, that means that Avogadro's number, that number of atoms in a mole is tied to mass somehow. So this definition of AMU, this is on your conversion sheet. This is true if we're talking about individual molecules or individual atoms. But there's a more useful way of thinking about AMU. 1 AMU is equal to 1 gram per mole. So if we have 4.72 times 10 to the 5 AMU here on this particular protein, if we had a mole of these protein molecules, it would be 47 kilograms. No, sorry, 470 kilograms. Because AMU is the same as grams per mole. So what does that mean when it comes to the periodic table then? All these atomic masses are conversions. They're going to let us convert between a mass that we can measure on a scale and the number of atoms in that system. So, one more point about mole. How come we only use moles for counting things in chemistry? How come we don't use moles in everyday life? How come you don't go to the store and buy a mole of eggs instead of a dozen of eggs? A dozen eggs. It's a lot. So if we work backwards, I use ping pong balls as a good way to think about atoms. They're round, they're kind of small. If we think about how many ping pong balls we could fit in this classroom, just really roughly, a ping pong ball is what, about an inch? And we could look up the actual dimensions if we wanted more sig figs, but let's call it an inch. Let's say that it's going to be, I don't know if that's 30 feet, then we'll call it 400 inches. 400 ping pong balls times 400 ping pong balls times, I don't know, half that, 200 ping pong balls. 400 times 400 times 200. We're going to get what? 400 times 400 is going to give me 160,000? Yeah. times 2, so 320,000. That's 3.2 times 10 to the 5. To get to 10 to the 23rd, we would need 10 to the 18 billion trillion, we would need a quadrillion classrooms. Basically, if you covered the surface of the earth in a mole of ping pong balls, it would be covered in a layer about a mile deep. It's an absurd number. So we really only use it when we're talking about really, really small things. Because that's the only way we can actually get a mole of anything, is to be talking about really small objects. All right, let's take a break. Let's come back at 11:30. We'll do some practice with this math.
I know. She went to a pageant. I won't put her on the I'm sorry. Okay. We'll go right now, but I wanted to talk about it. I was like, they posted something. I said, this is like 3 years ago. Dude, when you leave, I have this. Or do you keep this? Rody wrote a streak for my sweater that I wore. I like yours too. The blue I don't have nothing. I don't know where to get them. Soon,
It's-
be able to go through the.
It is, because you smell the coffee better. I don't like travel ones, because you can't smell the coffee.
It's
So,
cabinet.
yeah, Monday I left.
I think we took a couple more of these in there.
So I've.
Yeah.
Which
You did, if you want to hang out after. Are you scheduled for Labor Day?
No, I have to see it.
You have Monday, okay, yeah, just hang out afterwards, we'll do it. Does that sound good?
Yeah.
Yeah, there's a,
Thanks so much.
yeah, there's a link
No
in
problem.
this one. They have to fill that out.
Did you write this chart?
Let's export it. Yeah.
Wait, where do you go to get that?
The assignment,
Go to those.
and then it's like leaked.
Oh, the
It's a third
second.
thing.
What does this do?
Yeah.
Gotta get it on. How do you think you did on the midterm?
I only know 3 because I didn't study them.
Which one did you know?
The AT, but I thought I got that one.
Van
Yeah.
Vanappi.
I wrote.
You know how
BN.
she remembered it?
Voldemort.
Voldemort. He said Voldemort's bad.
Yeah. Okay, what about?
And
The
then
IN.
the IN.
In. Yeah.
Right? Into.
I put into scene, I didn't remember. I was in like anatomy mode.
This girl,
I have
the way she would remember.
No, that's like how
crack
to do it.
No, we would crack
You have to
stuff.
make it up ridiculous.
Like, I understand, but like, I don't know what her one was for lens. What does she,
Peanut butter.
what does she put on her peanut butter and jelly
Yeah.
sandwich?
No.
But I like got it and I was like,
Yeah.
I was like, okay, yeah, I'm like, whoa.
Where?
She wants to go to equity.
I already got those from equity. I want to go
She wants to go to promise.
That's promise.
let's go downstairs.
Hey, Sean, do you celebrate Mole Day?
Is it June 2nd?
October 23rd.
October 23rd. I do not usually, actually. Never gained much traction up here, so. The math department loves to make a big deal out of Pi Day, so I let them have Pi Day. They can do that. They don't have anything else. They're math people.
We had a Thai chem teacher in high school that was super into the mole molding. He made us make like actual moles out of like fabric and fill them up with beads and everything. That was like one of our projects.
Nice.
It's pretty funny.
That's my favorite type of mole.
Mole.
It's called a star-nosed mole, and it has like little tentacles around its nose for burrowing so that it can feel so it's a little bit like elephant trunks, but it's got a ton of them. They're terrifying.
Completely harmless.
Completely harmless for sure. That's probably endangered.
So a mole is an estimated unit.
I mean, it has a definition that's exact, but it's so many decimal places that it's basically useless to think of it as an exact number.
At which point though, would that mean that they can't individually measure atom?
So we're getting to the point where we can.
Oh, okay.
There are some research in very, very small systems has gotten to the point where we can actually image individual atoms or move around individual atoms. That's sort of the root of nanotech. You had heard that term. You can do
Yeah.
things like you can write. I think they did
a
some.
poem and with
Yeah.
individual atoms. That was kind of cool.
Yeah, so it's not the level that we're doing it commercially, but it's probably gonna start getting close in the next 10 years though, to be able to design electrical systems, electrical circuits using individual atoms. Potentially, and so it has a lot of potential for miniaturizing things, obviously. Has its own set of issues with that because electrons, when you get really, really small, they don't behave like current, they behave like electrons, which means now we're talking about quantum stuff.
Right.
But there's definitely some work in that area. So that's what makes me think though that they probably measured it down to the ones place. There's a possibility that they've measured moles down to the ones place.
Even then, the gram is an estimate too, right? I mean.
Right,
they would have
that's
well,
yeah,
you know, yeah.
exactly.
My thinking there was, it's like, so how do they even get a weight for an atom if they can't individually measure atoms to begin with?
Let's see, there it goes to. All these numbers are only going out to the, what is that, 9 sig figs? Wikipedia is a good place to, if you want to know the science history.
Yeah.
If you check out Wikipedia and read up on the history section, a lot of times it'll give you the background for where do they start and what were their original methods. Now we have more accurate methods to measure some of these things. But if you want the history behind it, that would be a good place, good first place to look. SI definition. Oh, okay.
Oh, it's new, interesting.
There you go, so in 2019. They redefined it to be that number exactly. So if you use all of those digits, it's an exact number.
Interesting.
So it's not exactly 12 grams of carbon anymore. I'm out of date. That line's key though.
Right.
As long as you're paying attention to your sig figs, then don't worry too much about it. This also gives me a good opportunity, since we're still missing 2/3 of the class at this point. So I won't start talking about the math just yet, but this is one of my favorite authors. Is a guy named Randall Monroe, who used to work. He's got a PhD in physics from Stanford. He worked on the robotics team for NASA for a long while. But the whole time he was doing that, both as a grad student working for NASA, he was writing a webcomic, which was called XKCD, just the letters XKCD. It's very nerdy. Some of it's funny, some of it's not. Some of it's like, I find them all funny, but I recognize not everybody has that drive of a sense of humor. But he also does a really cool blog that turned into a book called What If, where he just applies his knowledge of science to ridiculous questions. So for instance, what would happen if you were to gather a mole of moles in one place? So if you gathered a mole of moles in one place, he goes through, what I really like about this one in particular is he goes through how he does the back of the envelope calculation. Just making up, saying he's a physicist, not a chemist. He's not used to thinking in moles. But he does know that he can pick up a mole and throw it, which means he has an idea of how much a mole weighs. Something between 0 and 1 pound. Because if it was heavier than 1 pound, he wouldn't be able to throw it. So then he says, okay, well, if I say 1 pound is close to 1 kilogram, it's not that close, but it's close enough to get within a factor of 10 on our calculations. You basically say that a mole of moles is something like 1 trillion pounds. Trillion kilograms. Which is also roughly the same mass as the moon. So basically, if you had a mole of moles, the rodent, in one place, it would be about the mass of our moon. And then he puts some more numbers to it, you get a slightly more accurate number. It says it's a little bit over half the mass of our moon. So what would happen if you actually did that? Well, it turns out you would actually have something like a small moon. If you gathered them together above the surface of the Earth in orbit around Earth, we would have a new moon, roughly half the size of the other one. And then here's a good example. If we covered the Earth in a mole of moles, it would be higher than Mount Everest by a long shot. So anyway, there's a lot of other good stuff in here. And then he gets into the biology, what would actually happen to the moles, the animals. Moles in the middle would get crushed by the pressure and heat, turned into like mole goo. That would be kind of similar to what eventually turned into crude petroleum. But basically, If you wanna get a mole of moles, we have to go beyond Earth, because there's not a mole of moles on Earth. So if you wanna gather a mole of moles, you have to colonize this with a solar system first and spread moles everywhere. There's also some other really good ones. This is one of my favorite books, was this original book. In the cover, it's a drawing of a T-Rex being lowered into the Sarlacc from Star Wars. That big pit with the spikes. Somebody asked him what would happen if you dropped a T-Rex into the Sarlacc from Star Wars, and he actually went through, nerd lore and came up with an answer. He also looked at, what was the other one? Oh, what would happen if you could throw a baseball 99% the speed of light? It turns out at 99% the speed of light, the gas in our atmosphere can't get out of the way fast enough. And you actually wind up starting a fusion reaction on the front side of the baseball, which looks like a nuclear weapon went off. So basically you blow up the entire city with a crater centered on the pitcher's mound, if you actually threw a baseball that fast. So that sort of weird science questions are fun to you. I highly recommend this guy's books. I have some of them in my office. If you ever want to come borrow them, feel free. Let's get back to more relevant stuff though. If we know what that number is, that conversion between moles and atoms, that means it's pretty straightforward to actually get a number for atoms. From something like 1.54 moles of hydrogen, as long as we know 1 mole equals 6.022 times 10 to the 23rd of anything, we can say, okay, well, 1 mole is 6.022 10 to the 23rd atoms. Moles cancels moles. We get a number there. And it's going to be something like 9 times 10 to the 23rd, right? Just under 9 times 10 to the 23rd. So this is just another conversion. It's a weird one because it's a counting number, but it's really no different than any of our other conversions. One thing I will note, you have to write MOL for your abbreviation for moles. Saves you a whole letter. You can't write M because M is meters, right? You can't write MO because MO is months or molybdenum. So you have to write MOL. Just like the abbreviation for minutes is MIN, you have to write MIN. You can't just write MI. So make sure you write it that way. And it's a unit we're not familiar with, but you can't just write capital M, because capital M is a concentration unit that is moles per liter. So it's kind of like a density. So don't use capital M for this. It's got to be MOL. Doesn't save you that much time, but it's a way to make sure we don't confuse ourselves. If I wanted to go the other way, if I said let's go back to that number or that question from problem 4. I want to know how many moles of neutrons this is, instead of just how many neutrons. 1.365 times 10 to the 20. Well, in this case, our counting number goes on bottom. So 10 to the 23rd neutrons is 1 mole of neutrons. So we divide if we're going that way. This also is another good time to remind you to be really careful with parentheses and order of operations notation. Because if I took this number, if I was gonna plug this into a calculator, you could type it in as 1.365 times 10 caret 20 over 6.022 times 10 caret 23. If you just write it in like that, you're gonna get the wrong number. Because when you're doing order of operations, you do the exponents first, but then multiplication and division are really the same step in PEMDAS. Because division is just multiplying by 1 over something. So what happens on your calculator when you type it in this way is you get 10 to the 20th and 10 to the 23rd. But then it's gonna take this 1.365 number times 10 to the 20th, that's all fine. It's gonna take that number, divide by 6.022. And get a number for it, and then it's gonna take that number and multiply by 10 to the 23rd. Basically, you're gonna wind up with a number that's really, really big, something like 10 to the 43rd. If you just type it in like this. If you do that, that's telling your calculator do all of this math before you do the division. So with scientific notation, you either have to write it out with parentheses. It doesn't really matter if you have parentheses at the beginning, but if you want to get in the habit of putting parentheses around every scientific notation number, it's not a bad habit. Because that's gonna make sure it does that math and turns it in, rewrites it as a whole bunch of digits instead of scientific notation before it does the division. Okay, the other way that you can type this in is to use that key on your calculator. That uppercase E button has to be the uppercase one, not the lowercase e. Lowercase e is an irrational number like pi, it's 2.71 something. Uppercase E is the shortcut, and some calculators, especially the ones that come pre-programmed on your smartphones, they don't differentiate between the E's, which is really confusing for those of us in the sciences. So you have to be really careful which button you're using. But so the way I would type this in would be 1.365 E20. Right? This whole section times 10 to the gets abbreviated as with a capital E. Right, so find that button on your calculator. Because the other thing that this button does is it automatically puts those parentheses around it. You don't need to worry about the parentheses as much if you're using this. So this will give you the right answer. So will this. And if your calculator, the calculator you're used to using, doesn't have this E button, you don't need it. It just saves you time. And so then our final answer, we have a big number divided by an even bigger number. So with that in mind, should our answer be greater than 1 or less than 1? Less than 1. Big number divided by an even bigger number should be less than 1. Difference of 10 to the 3 here, so probably like 0.00 something. Maybe 0.000 because this is also bigger than that, so. You say it louder, Jacob, it's like
6.
2, 6, 6, 7. Perfect. Number of weeks. And half the time you're making some.
Wait, no.
Oh, so it's it's 2.36.
We're not gonna keep all those digits though, right? So
See.
4 sig figs, we'll keep 4 sig figs. Might as well put it back in scientific notation. 6, 7. There it is. So it's still a number in scientific notation, but it's one that's a little bit easier to wrap our head around than times 10 to the 20, right? 0.0002, a lot easier to think about as a number than anything times 10 to the 20. All right. So doing this kind of math, not too tricky. Very rarely am I actually gonna ever ask you about how many atoms anymore. Now that we know what a mole is, pretty much everything from here on out is gonna be in moles. Because we don't wanna think about individual atoms. Physicists think in individual atoms for some of their experiments because they're talking about some of the fundamental derivations of some of their units. And they're talking about individual atoms. For the most part, we do everything on the mole scale in chemistry though. So we're only gonna think in moles from here on out. I think probably the one time that you might see another question about tell me the individual atoms might be on a quiz where I ask you just to show me you know how to do this math. Basically, once you know how to do this math, we're not gonna do it again. All right. Here's the other useful calculation here. And I already mentioned this once. If we have, and we did just find out during break, that they redefined this number, Avogadro's number, that number of the atoms in a mole has been redefined to not be based on exactly 12 grams of carbon-12 anymore. They changed that back in 2019 and flew under the radar somehow, so I didn't notice it. Doesn't really matter, it's still gonna be really close to the number of atoms in 12 grams of carbon. But what that gives us is a conversion from AMU per atom is the same as saying grams per mole. So if you look at your periodic table, where it has the atomic mass written for everything, that is the mass of a single atom. So we use lead again. Lead is 207.21. Yeah. So PB, atomic number 82, mass 207.21. There's its box on the periodic table. That means if you picked a lead atom at random on Earth, the average lead atom weighs 207.21 AMU. That I say the average lead atom because really that's a mixture of more than one isotope. So some of the isotopes are going to be lead 207, some of them are going to be lead 208. On average though, if you picked 100 lead atoms and averaged their mass, it would be about 207.2 AMU. But we don't like AMU per atom because we don't want to think about per atom. We want to think about per mole. The nice thing about this is it means the way they define these units is 1 AMU is equal to 1 gram per mole. So what that means, if I have 207.21 grams of lead, that's a number I can measure, right? That's not an absurdly small number. If I have lead and I have 207 grams of lead, that's approximately 1 mole of lead atoms. Okay, so this is just another conversion, but it's a conversion that lets us go from a measurable number into a number of atoms that we could count. It's a really big number, but it's still just a number of atoms. So let's try this. We're gonna use our periodic tables as a conversion sheet here. If you have 0.5 moles of gold, what does that weigh? In terms of grams? Let's give it a few more things. We'll call it 0.500 moles. Weigh. And so straight from the periodic table, the atomic masses on the periodic table are a conversion. So the fact that the mass number for gold on the periodic table is 196.967 tells us 1 mole of gold equals 196.967 grams. So that's just a conversion now. So 0.500 moles AU. 1 mole AU is 196.967 grams. Ish. 98. Oh, 98. I went the wrong way. 98.5. So for the second one, 55.4 moles of carbon. It's carbon now, not gold. So we're gonna get a different number for the mass. We check your periodic table. You can see that the mass number for carbon is 12.011 grams. Whatever your mass number is on the periodic table is your conversion. So then we get moles of carbon, cancels out moles of carbon, we get grams of carbon. So we're gonna get something like 600.
665.
665. Are these atomic masses on the periodic table, are they measured?
Yes.
Why, Corbin?
They're an estimate.
Is there an estimate? Yeah, because different periodic tables will have different number of decimal places. If I look up if I just use a search engine to find the atomic mass of carbon, if I check a reputable source and don't trust what Google tells you when you just throw it into Google search engine or ChatGPT. Because what will frequently happen is the way that both ChatGPT and Google try to answer questions like that, if you ask them what a number is, sometimes they get it right, but often they miss often enough that you want to be really careful with that, trusting them to, because whatever page Google grabs the mass of carbon from, it's gonna be full of other numbers. And Google and other AI are not good enough at knowing which of those numbers it's supposed to grab. So usually it would be right, but you can't trust it. Oddly enough, when I was in high school and in college, Wikipedia was seen as being like the most unreliable possible source that you could possibly use to look up a number. And now it is way more reliable than what most people are using. And in general, Wikipedia is actually pretty useful for this because if you look at Wikipedia, it'll have its sources on here. Here's its standard atomic weight. Here's 12.011 plus or minus 0.002. Not only does it give you the uncertainty associated with it, it also provides a source. Atomic weights of the elements from the IUPAC technical report. That's a really reputable source. If you really want to cite something that's not Wikipedia, look it up on Wikipedia and you go to Wikipedia's source and you make sure that Wikipedia's source says the same thing that Wikipedia says. Odds are it's trustworthy, especially on stuff in the sciences. When you get into the history, politics, economics realm, there's a lot of back and forth. It was actually really interesting this was back in what, 2016. If you watch the edits happening in real time to Wikipedia pages during the debates between Donald Trump and Hillary Clinton, it was wild. There were thousands of people that were rooting for their political party that were in Wikipedia in real time, changing data in Wikipedia in real time to make it match what their candidates were saying. So when it gets to political things, and to some extent, historical things, you have to be careful about who's editing, and you really do need to follow the sources that Wikipedia is using to see if they're useful. But in the sciences, nobody cares that much. Nobody is making their political platform the atomic mass of carbon-12. So for the most part, these are pretty useful sources of information. Way better than just throwing it into the search engine. What's the atomic mass? If you're going to use a search engine for that, you can get away with using Wolfram Alpha. Wolfram Alpha actually has atomic masses programmed into it, but it's not because it's not really an AI. It actually just has all of the periodic table programmed into it. And so it does an okay job. But better still is your periodic table or Wikipedia in looking at their sources. All right. Okay. Let's go the other way. If I have 0.795 grams of silver, and I want to know how many moles of silver that is. We're still going to go back to the periodic table. We're still going to use the atomic mass. It's just going to be flipped over now. Because when we look this up, we can say, okay, well, 1 mole of silver. It equals 107.88. I'm right there, so I have it. Oh. So if that's our conversion, we just need to structure it so that grams cancels out grams. So we're going to write it as 107.88 grams is 1 mole of silver. Okay, so you all knew without showing your work as a conversion that I'm supposed to multiply by 21 on that problem from last week's quiz, right? How did you know to multiply instead of divide? it gets a little bit tricky. We wanna set it up so that if you show it like this, it gets really obvious whether you're supposed to multiply by the atomic mass or divide by it. You need the units to cancel out. So if I'm in grams of silver and I wanna cancel out grams of silver, grams has to go on bottom.
That's enough.
0.008-ish. 7.3.
Now. 74. 74.
How many sig figs do we wanna keep though? That's a measured number, so is that, so that's 3 sig figs, leading zeros don't count as sig figs. So 7.3,
Oh.
7.47,
What? Yeah.
Yeah, 7.
Wait, wait. Just seven, wait, 0.00736.
the if we're keeping 3 sig figs, that would be 0.00737. Because the calculator answer was,
Wait.
right, so. Turn that into a 7. Again, don't get too hung up on having the exact same numbers, as long as you're the same within sig figs, as long as you're only off by 1 in this last digit. Then you're probably fine, maybe you plug in 107.9 instead of 107.88. Could be enough to throw you off a little bit in that last digit.
Just to make sure I'm really clear on it. So the atomic mass of an element is equal to 1 mole of the average isotope of that element weighed in grams.
Correct.
Okay. And I still don't understand the conversion to the AMU and atom that you had a few slides ago.
Okay, so the question was about, for all intents and purposes, we don't need to worry about AMU too much, as long as you know 1 AMU is the same as 1 mole per, or 1 gram per mole.
Okay, that makes sense.
So AMU is if we're talking about it in terms of individual atoms, but they chose the definition of an AMU such that 1 AMU per atom is equal to 1 gram per mole.
What is a gram per mole?
So if we. Let's use hydrogen, 0.008 gram AMU. Per 1 atom. Way they defined an AMU is basically a gram divided by 6 times 10 to the 23rd. So we can say, okay, well, that means that 6.022 times 10 to the 23rd AMU is equal to 1 gram.
And then you convert that into, okay.
So that's, so, but then the other side, that would give you grams per atom. That'd be a really small number, right?
Right.
But the other side we can do is we can say 6.022 times 10 to the 23rd atoms.
It's your moles, right? Yeah, right, okay.
Those numbers cancel out, so you get the same thing. Atoms per moles,
That's the same.
AMU per atom is equal to grams per moles.
Okay, that makes perfect sense. Thank you.
All right. We want to do more math right now, or do we want to save the math and learn how to name things? We talk about ions. I've seen about a 50-50 mixture, so I'm gonna go with the one that's gonna prep us for the quiz this weekend a little bit better. We'll give the math a break. Come back to this on Monday. All right. We're gonna start talking about compounds more now. So elements are all great. As long as you have your periodic table, you know a lot about every element. You know how many protons and neutrons it has, you know how many, what the mass is. We had used this as a conversion sheet. What happens once we start getting past individual elements and start talking about compounds? Well, for starters, we have to understand why compounds form in the first place. Why doesn't everything just stay in its elemental state? If we have sodium as a metal, when sodium has a charge of 0, it's got 11 protons and 11 electrons, right? Do we ever see sodium as a metal in the real world? What do you think of when you think of sodium? Table salt. Because it turns out the electron configuration for sodium is not super stable. If we look at those orbitals, so for sodium, remember this was energy, we had 1s, 2s, 2p, 3s. If we're trying to add in all of our electrons here, that's 10. Sodium's electron configuration looks like that, right? Or if we're writing it out as the electron configuration, 1s2, 2s2, 2p6, 3s1. Why doesn't it stay like that? I mean, if we kept it away from absolutely everything else, we didn't let it touch anything else, kept it in a vacuum, it would stay like that. In fact, we have sodium metal in the lab, in the stock room. We're gonna do a lab where I'm gonna show you what happens when you let sodium metal get exposed to water. It turns out that it explodes. That's gonna be one of the ones that I do it for you. Well, why is that? It turns out it's because of these valence electrons. Almost everything that changes in chemistry is because of the valence electrons. This one valence electron that sodium has is super unstable on its own. The reason that it's unstable is because all of our orbitals and all of our electrons are way more stable, way happier, for lack of a better term. I think stable is the better term. When you only have completely filled or completely empty orbitals. So we can empty out the entire third energy level if this sodium just gives away an electron. If sodium gives away an electron, the sodium gets much more stable. There's other elements out there that are trying to gain electrons, right? If we look at, say, oxygen. Oxygen has a total of 6 electrons, right? No, 6 valence electrons, 8 electrons. So oxygen's electron configuration is still gonna be 1s, 2s, 2p. So it's gonna look like that. Oxygen is almost to having a full valence. If oxygen can just gain a couple of electrons, oxygen can be really stable too. So the reason that sodium metal doesn't react when it's by itself in a vacuum and nothing's allowed to touch it is because it doesn't have anything it can give an electron away to. Oxygen is relatively stable as long as you don't let it react with anything. Because oxygen, to become more stable, needs to gain electrons. If you don't expose it to something that has extra electrons to give, it stays the way it is. But things get more stable once we can allow them to have full orbitals, full energy levels. So sodium is gonna get more stable by giving away one electron. Oxygen is gonna get more stable by gaining 2 electrons. So that means that the most stable ion for sodium is gonna be a +1 charge. Sodium gets more stable when it's got a +1 charge. Oxygen gets more stable when it has what charge? It needs to gain 2 electrons and the electrons are negative. So oxygen gets more stable when it's got a -2 charge.
For the sodium, wouldn't it also be stable with the electron?
So if you gave sodium an extra electron, then we can fill the 3s, but we still haven't filled the 3p. And filling up an s orbital, because the s orbital is so small, is not as big of a stability bonus.
Okay,
So generally speaking, we're gonna try and get rid of electrons.
so it's more about the power levels than the individual.
Yes, that's the most important factor is those energy levels. All right, everybody look at your periodic table. Everybody see that stair step line? That starts at the P block next to boron and goes down towards the bottom right corner. That's our dividing line between metals and non-metals. With
Where?
the stair step line, see there's the bolded line right there? Everything to the left of that line is a metal. Everything to the right of that line is a non-metal. The way we define that is based on how they get more stable on Earth. And in general. And all of the metals become more stable by giving away electrons. All of the non-metals get more stable by gaining electrons. So Torben, to go back to your question about why doesn't it just do this? It's a metal, and metals usually are going to be trying to give away the electrons because that's going to get them to empty out that valence shell.
Okay,
And if you look at, that means that most of the periodic table, including the F block, are metals. There are way more metals than there are anything else on the periodic table. But if you look at the things that are non-metals, it's a lot of stuff that we have in large quantities on Earth. Earth in particular has a lot of oxygen, has a decent amount of nitrogen, a little bit of carbon. All of those non-metals react with the metals to form pretty much all of the rocks and minerals and all of the hydrosphere and lithosphere that we have on Earth. Basically, everything that's not living on Earth is mostly made up of metals and non-metals that are reacting together so that your metals can give away electrons and your non-metals can take the electrons. So what does this mean about the periodic table? It means that we can actually, if we know that the periodic table is based around electron configuration, it means we can guess what the most stable charge is going to be for everything as well. We just look at where it is on the periodic table and say, okay, well, everything in column 16, the one that starts with oxygen, is going to be trying to gain 2 electrons to become more stable. So the elements in that column, oxygen, sulfur, and selenium, will gain 2 electrons. So we can expect to them, when they're stable, they're gonna have a -2 charge. So counting valence electrons is kind of helpful in terms of checking your electron configuration. Why does it matter? Because it predicts what the charge will be of those when they're stable. So sodium gets more stable when it's a +1 charge. Oxygen gets more stable when it's a -2 charge. If we let sodium as a metal give away its electrons to oxygen, how many sodiums does it take to give oxygen enough electrons to be stable? I'll say that again. Oxygen needs to gain 2 electrons. Each sodium is trying to give away a single electron. So that means each oxygen needs 2 sodiums to react with. The other way you can think about it is if you know the charge, stable charges of the ions, we want those charges to add up to 0 in order to make a stable compound. For it to be a stable compound, we need 2 sodiums for every 1 oxygen. Because if we have 2 Na pluses and 1 oxide with a -2 charge, that's gonna add up to a charge of 0, and that's gonna give us an ionic compound. An ionic compound is just what you get when you let things with opposite charges sort of stick together. You got a plus charge here and a minus charge there, opposite charges attract. So if you know what the charges on the ions are, we can predict what's gonna stick together. Anything with a positive charge is gonna stick to something with a negative charge. And they're gonna stick together in the ratio that lets their charges add up to 0. So 2 sodiums for every 1 oxygen. Let's see. So anytime you have an ionic compound, it's gonna be a metal, because metals try to have a positive charge. And a non-metal, because non-metals are gonna have a negative charge. And that formula that you're gonna make is just gonna be whatever lets the charges add up to 0. So you just need your periodic table in order to figure out what those charges are. What's the stable charge on calcium going to be? Look at calcium on the periodic table. A good guess. It's got 2 valence electrons, so it can give away 2 valence electrons. So calcium, when it's stable, is gonna be a 2 plus. Oxygen, when it's stable, we already just talked about that one, right? So how many oxygens and calciums do we need to add up to 0? 1 of each. So the formula for calcium oxide is just CaO. Watch your capitalization.
So you can actually predict the majority of the compounds without having to actually make them.
Exactly. So sodium and chlorine, there's table salt. What's the charge on the sodium? When it's charged as Na with a plus, right? When it's stable. What's the charge on chlorine going to be?
And it's just 1.
It only needs to gain 1 electron, so -1. So sodium chloride, the 1-to-1 ratio. All right. Where's the slide that I want? This one. So here's the trick with this. When it comes to predicting these charges, the vast majority of the periodic table doesn't have predictable charges though. The ones that we care about the most do. The non-metals, we can predict their charge pretty well. The first 2 columns, we can predict their charge pretty well. +1, +2. -1, -2, -3. But these ones in the middle get a little bit tricky. Those are the ones that somebody asked about earlier, where we talked on Monday about things that can have more than 1 stable charge. These transition metals. Which is basically all of the metals except for these ones in the first 2 columns. can have more than one stable charge. So iron can be stable as a +2 or a +3. Copper can be stable as a +1 or a +2. Nickel can be stable with, it has like 5 stable charges. Chromium has like 5 stable charges. So for those ones, we can't predict the charges necessarily. But the ones I want to focus on are these first 2 columns, because these ones, the first column's always going to be +1 when it's stable. Second column's always +2 when it's stable. No d orbitals involved, so none of the weird stuff. These ones that I've outlined here, those ones only make one stable charge. So basically, these are the ones that we want to be able to predict their charge with as well. I'm going to teach you how to talk about these other ones next week, so that we can say specifically it's an iron with a +2 versus an iron with a +3. But these 6 right here and these first 2 columns are the ones we can always predict their charge. So I know we're almost done. Let's talk about aluminum real quick. How many valence electrons does aluminum have? Total of 3, right? It's got 2 electrons in the 3s orbital and it's got 1 electron in the 3p. So what would we expect aluminum to be stable? What kind of charge would we expect aluminum to be stable with? Plus what? +3. If we can empty out that third energy level, then it's super stable all of a sudden, because now it looks like neon. Right? It's got 10 valence electrons and they're all filling up the 1s in the second energy level. So aluminum and gallium and indium, when they're ions, they're always +3s. Because gallium and indium have d orbitals involved, which sometimes makes things complicated. But in this case, the d orbitals are full. And if the d orbitals are full, we're not going to break them up. So for aluminum, gallium, and indium, they're always +3s when they're an ion. So with that logic, what about zinc and cadmium? Zinc has a full d orbital, cadmium has a full d orbital, 2 valence electrons, right? So zinc and cadmium, when they're stable, are +2s. Seeing a pattern here? +3, +2. Silver is a weird one. Just a +1. Silver's electron configuration is non-standard. It's an exception. Silver's electron configuration looks like argon. Sorry, krypton. 5s1 4d10. Because that gives us the opportunity to fill a d orbital. So it's weird, and that's why it's only a +1. Only ever stable with a +1, because by stealing an electron from the 5s and putting it into 4d, we get to fill that orbital. All right. Quiz will open at noon tomorrow. It's going to be counting valence electrons and predicting charge. So no math on this quiz this weekend. Do it yourself, don't Google it. Better.
Wait, the quiz is counting valence electrons and what else?
And charges, like we just did.
Okay, perfect.
So, it's her, 5 seconds.